Good morning students. Welcome to 11th standard chemistry video class. We are discussing lesson 10 chemical bonding. In our last video class we completed up to formal charges. In this video we will start with the next topic, Lewis structure for exception to octet rule. Lewis structure for exception to octet rule. Already we know that what is octet rule. That is having 8 electrons in their valence shell. The octet rule is useful for writing Lewis structures for molecules with second period elements as central atoms. The second period elements namely lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. In some molecules, the central atoms have less than 8 electrons around them, while some others have more than 8 electrons. Here, the exception to the octet rule can be categorized into following three types. First one, molecules with electron deficient central atoms. Second one, molecules containing odd electrons. Third one, molecules with expanded valence shell. Let me discuss one by one. First one, molecules with electron deficient central atoms. Consider the example boron trifluoride with the formula BF3, in which the central atom is boron, which contains 3 valence electrons, where each fluorine atom contains 7 valence electrons. Hence, the Lewis structure for boron trifluoride is shown here. Since boron is surrounded by 6 electrons, hence one of the fluorine atom gives a lone pair of electrons to boron and forms a additional bond. Hence, it is shown in the picture. However, the above structure is unfavorable as the most electronegative atom fluorine shows positive formal charge. Initially, the structure with the incomplete octet is the favorable one. Hence, the molecules like boron trichloride with the formula BCl3 and beryllium chloride with the formula BeCl2 also have incomplete octet. That is, they should not contain 8 electrons. Second one, molecules containing odd electrons. There are some molecules, the central atom with an odd number of valence electrons. For example, nitrogen dioxide with the formula NO2 and nitric oxide with the formula NO. In both the structures, the central atom is nitrogen. Hence, nitrogen atom contains odd number of valence electrons. Hence, in nitrogen dioxide and nitric oxide, all the atoms does not have octet configuration. The Lewis structure of the above molecules are shown here. Here we are having Lewis structures of nitric oxide and nitrogen dioxide with formal charges. Third one, molecules with expanded valence shells. In molecules such as sulfur hexafluoride with the formula SF6, phosphorus pentachloride with the formula PCl5, the central atom has more than 8 valence electrons around them. Here, the central atom can accommodate additional electron pairs by using outer vacant d orbitals. In sulfur hexafluoride, the central atom sulfur is surrounded by 6 bonding pairs of electrons, that is 12 electrons. It is shown here. In phosphorus pentachloride, the central atom phosphorus is surrounded by 5 bonding pairs of electrons, that is 10 electrons. It is shown here. Hence, we completed the topic Lewis structure for exception to octet rule. Next topic, ionic bond or electrovalent bond. Let us consider two combining atoms with different electronegativity values. One atom with least electronegativity value and another atom with high electronegativity value. The atom with least electronegativity value loses one or more electrons and forms cation. The atom with high electronegativity value gains one or more electrons and forms anion. Hence, both these atoms can attain the nearest inert gas electronic configuration. Hence, both cation and anion are held together by the electrostatic attractive force, which is known as ionic bond or electrovalent bond. Or otherwise, a complete transfer of valence electron from one atom to another atom creates cation and anion. Here, this cation and anion held together by the electrostatic attractive force is said to be ionic bond or electrovalent bond. The formation of ionic bond is explained by taking an example. Let us consider the formation of potassium chloride. The electronic configuration of potassium and chlorine are given here. Potassium with the symbol K. The atomic number is 19. Its electronic configuration is stable electronic configuration of argon 4s1. For chlorine, the symbol is Cl. The atomic number is 17. Its electronic configuration is stable electronic configuration of neon 3s2 3p5. Here, potassium has one electron in its valence shell, where chlorine has 7 electrons in its valence shell. In order to attain inert gas electronic configuration, potassium loses its valence 1 electron and attains the stable electronic configuration of argon and becomes unipositive potassium cation, that is K+. Next one, in order to attain inert gas configuration, chlorine gains 1 electron and attains stable electronic configuration of argon and becomes uninegative chloride anion, that is Cl-. These two ions, namely K+ ion and Cl- ion, combine to form an ionic crystal KCl, that is potassium chloride. Hence, these two ions K+ and Cl- are held together by electrostatic attractive force. This electrostatic attractive force is said to be ionic bond or electrovalent bond. Therefore, ionic bond is formed between K+ and Cl- ion. The energy required for the formation of 1 mole of K+ ion is 418.81 kilojoule. This energy is called ionization energy. The energy released for the formation of 1 mole of Cl- ion is minus 348.56 kilojoule. This energy is called electron gain enthalpy. Hence, the sum of these two energies is positive. The value is 70.25 kilojoule. During the formation of potassium chloride from its constituent ion, the amount of energy released is 718 kilojoule. This favors the formation of KCl and its stability. Hence, we completed the topic ionic bond or electrovalent bond. Next topic, bond parameters. A covalent bond is characterized by parameters such as bond length, bond angle, bond order, etc. A brief description of some of the bond parameters is given here. Let us discuss one by one. First, we will start with bond length. Bond length. Here, we are having the definition for bond length. The distance between the nuclei of the two covalently bonded atom is called bond length. It is an important question. If they ask define bond length, you have to give this answer. Consider a covalent molecule A bond B. Here, this molecule is formed from atom A and atom B, in which radius of atom A is Ra, radius of atom B is Rb. Hence, the bond length is given by the sum of the radii of atom A and atom B, that is Ra plus Rb. It is shown here. Here, the bond length for the given molecule AB is addition of Ra and Rb. It is given by Ra plus Rb. The bond length can be determined by spectroscopic, X-ray diffraction and electron diffraction techniques. The bond length depends on the size of the atom and number of bonds between the combining atoms. Consider the size of the atom. Greater the size of the atom, greater will be the bond length. Consider the following examples. Carbon single bond carbon and carbon single bond nitrogen. In carbon single bond carbon, the size is greater. Hence, the bond length value is greater, that is 1.54 Armstrong. Where carbon single bond nitrogen, the size is smaller. Hence, the bond length value is smaller, that is 1.43 Armstrong. Next one, consider number of bonds between the combining atoms. If the number of bonds between two atoms increases, the bond length value decreases. For carbon single bond carbon, the bond length value is 1.54 Armstrong. For carbon double bond carbon, the bond length value is 1.33 Armstrong. For carbon triple bond carbon, the bond length value is 1.20 Armstrong. From the above, it is understood that number of bonds between combining atoms increases, the bond length value decreases. Next topic, bond order. Here, we are having the definition for bond order. The number of bonds formed between the two bonded atoms in a molecule is called a bond order. It is an important question. If they ask define bond order, you have to give the first three lines. In Lewis theory, the bond order is equal to the number of shared pair of electrons between the bonded atoms. If only one pair of electrons is shared between two atoms, it forms single bond. Hence, the bond order is 1. If two pairs of electrons are shared between two atoms, it forms double bond. Here, the bond order is 2. If three pairs of electrons are shared between two atoms, it forms triple bond. Here, the bond order is 3. For hydrogen molecule, there is only one shared pair of electrons and hence it forms single bond and the bond order value is 1. Similarly, in H2O, HCl, methane, etc., the central atom forms single bond with bond order of 1. Here we are having the bond order of some common bonds. In these examples, the number of bonds formed between two combining atoms indicates the bond order value. It is shown here. Next topic, bond angle. Here we are having the definition for bond angle. Generally, covalent bonds are directional in nature and are oriented in specific directions in space. This directional nature creates a fixed angle between two covalent bonds in a molecule, and this angle is termed as bond angle. It is also an important question. If they ask define bond angle, you have to give the first 6 lines, or otherwise the angle formed between two covalent bonds in a molecule is said to be bond angle. It is usually expressed in degrees. The bond angle can be determined by spectroscopic methods and it can give some idea about the shape of the molecules. Here we are having the bond angles for some common molecules. Methane, the formula is CH4. The bond angle between hydrogen, carbon, hydrogen is 109 degree 28 minutes. Next, ammonia with the formula NH3. The bond angle between hydrogen, nitrogen, hydrogen is 107 degree 18 minutes. Next, water. The formula is H2O. The bond angle between hydrogen, oxygen, hydrogen is 104 degree 35 minutes. Next topic, bond enthalpy. Bond enthalpy, otherwise called bond energy. Here we are having the definition for bond enthalpy. The bond enthalpy is defined as the minimum amount of energy required to break 1 mole of a particular bond in molecules in their gaseous state. It is also an important question. If they ask define bond enthalpy or bond energy, you have to give the first 4 lines. The unit of bond enthalpy is kilojoule mole power minus 1. Larger the bond enthalpy, stronger will be the bond. Again I repeat, larger the bond enthalpy, stronger will be the bond. Here the bond energy value depends on the size of the atoms and number of bonds between the bonded atoms. Larger the size of the atom involved in the bond, lesser is the bond enthalpy or bond energy. In case of polyatomic molecules with 2 or more same bond types, the term average bond enthalpy is used. Consider water molecule with the formula H2O. It contains 2 OH bonds. For breaking first OH bond, the energy required is 502 kilojoule mole power minus 1. For breaking second OH bond, the energy required is 427 kilojoule mole power minus 1. Therefore, the average bond enthalpy of OH bond in water is given by 502 plus 427 divided by 2, which is equal to 464.5 kilojoule mole power minus 1. This tabular column gives the bond lengths and bond enthalpies of some common bonds. Hence, we completed some bond parameters, namely bond length, bond order, bond angle, bond enthalpy. Let me stop up to this topic. The remaining topics that we will discuss in our next video class. Thank you.